Sharing neutrals between multiwire branch circuits, as described with two separate 120 volts 20 amp circuits using a common 12-gauge neutral, is generally not permissible according to the National Electrical Code. The primary concern revolves around safety and the potential for overloading the neutral conductor. Section 300.13 of the NEC addresses the continuity of the neutral conductor and, by extension, the limitations on sharing neutrals in multiwire branch circuits. The code generally prohibits the sharing of neutrals between multiwire branch circuits unless specific conditions are met. These conditions typically involve ensuring that all circuits sharing the neutral originate from the same phase and are protected by a device that opens all ungrounded conductors simultaneously, such as a double-pole circuit breaker or handle tie. In a standard 120 volts/20 amp circuit, the neutral conductor carries the unbalanced current back to the source. When two separate 120 volt circuits share a neutral, the neutral conductor could potentially carry the combined current of both circuits. If both circuits are loaded to their maximum capacity of 20 amps each, the neutral conductor would be carrying 40 amps. This can lead to overheating of the neutral conductor, insulation damage, and potentially a fire hazard, especially if the neutral conductor is not properly sized to handle the combined current. The code requires that the neutral conductor be sized to carry the maximum unbalanced load. In a multiwire branch circuit, the neutral only carries the difference in current between the two hot legs, but in the scenario described, there is no guarantee of balanced loading. The NEC defines a multiwire branch circuit as a circuit consisting of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, which is connected to the neutral conductor of the system. Multiwire branch circuits are commonly used to provide both 120 volts and 240 volts from a single 3-wire cable. In a properly configured multiwire branch circuit, the neutral conductor only carries the unbalanced current. For example, if one hot leg is carrying 10 amps and the other is carrying 15 amps, the neutral will only carry 5 amps. However, if the two circuits are not part of a multiwire branch circuit and instead are two separate circuits sharing a neutral, the neutral could carry the full load of both circuits. The absence of a handle tie or common yoke linking the circuit breakers is a critical safety concern. Without a handle tie, it is possible for one circuit to be de-energized while the other remains energized. If someone were to work on the de-energized circuit, they might assume the entire circuit is dead, not realizing that the shared neutral is still energized by the other circuit. This could lead to electric shock or electrocution. The distance between the devices, 50 feet, does not mitigate the hazard. The entire length of the shared neutral is subject to potential overloading and the risk of being energized unexpectedly. The fact that several electricians insist this is acceptable does not make it so. It is crucial to adhere to the NEC and other applicable codes and standards. If there is any doubt, it is always best to consult with a qualified electrical inspector or engineer. To correct this situation, the shared neutral should be removed and separate neutral conductors should be run for each circuit. Each circuit should have its own dedicated neutral conductor that is sized appropriately for the load. This will ensure that the neutral conductor is not overloaded and that the risk of electric shock is minimized. In addition to the safety concerns, sharing neutrals in this manner can also create problems with circuit performance. The voltage drop on the neutral conductor can be excessive, which can cause appliances and equipment to malfunction. It can also create noise on the neutral conductor, which can interfere with sensitive electronic equipment. Therefore, it is not acceptable to feed two separate 120 volts, 20 amp circuits from a common 12-gauge neutral. The NEC prohibits this practice, and it creates a significant safety hazard. It is important to always follow the NEC and other applicable codes and standards to ensure the safety of electrical systems. Here is a more detailed explanation of why sharing neutrals in this scenario is dangerous and violates the NEC. Firstly, overload potential. When two separate 120 volt circuits share a single neutral, the neutral conductor can become overloaded if both circuits draw their maximum current simultaneously. For instance, if each circuit is rated for 20 amps, the neutral could potentially carry up to 40 amps. This exceeds the ampacity of a typical 12-gauge wire, which is generally rated for 20 amps. Overloading the neutral can cause it to overheat, leading to insulation damage, a fire hazard, and potential failure of the electrical system. Secondly, violation of NEC Section 300.13. This section of the National Electrical Code NEC addresses the continuity of the grounded conductor neutral. It requires that the neutral conductor remain intact and unbroken throughout the circuit. Sharing a neutral between two unrelated circuits violates this requirement because it compromises the integrity and safety of each individual circuit. Thirdly, risk of unequal current distribution. Even if the total current does not exceed the ampacity of the neutral conductor, unequal current distribution between the two circuits can create problems. If one circuit draws significantly more current than the other, the neutral will carry a disproportionately high current, potentially causing voltage imbalances and affecting the performance of connected devices. Fourthly, safety hazard during servicing. When working on one of the circuits, there is a risk of electric shock if the other circuit is still energized and sharing the neutral. An electrician might mistakenly assume that the entire circuit is energized when only one of the hot wires is disconnected. The shared neutral can still carry current from the other energized circuit, posing a safety hazard. Fifthly, potential for harmonic distortion. In modern electrical systems, nonlinear loads such as electronic devices and LED lighting can introduce harmonic currents into the neutral conductor. When multiple circuits share a neutral, these harmonic currents can accumulate, leading to excessive neutral current and potential overheating. Sixthly, incompatibility with ground fault circuit interrupters. Ground fault circuit interrupters (GFCIs) are designed to protect against electric shock by detecting imbalances in current between the hot and neutral conductors. Sharing a neutral between two circuits can interfere with the proper functioning of GFCIs, rendering them ineffective and increasing the risk of electric shock. Seventhly, lack of common disconnect. Without a common disconnect, such as a handle-tied circuit breaker, it is impossible to simultaneously energize both circuits sharing the neutral. This makes it difficult to safely perform maintenance or repairs on either circuit, as there's always a risk of one circuit remaining energized through the shared neutral. Eighthly, code compliance issues. Sharing neutrals in this manner violates several NEC requirements, which can lead to code compliance issues and potential fines or penalties. Electrical inspectors typically flag such installations as non-compliant due to the safety risks involved. Ninthly, increased voltage drop. When a neutral conductor is shared between multiple circuits, it can experience increased voltage drop, especially under heavy load conditions. This voltage drop can negatively affect the performance of connected devices, causing them to operate inefficiently or malfunction altogether. Tenthly, difficulty in troubleshooting. Sharing neutrals can make it more difficult to troubleshoot electrical problems. If there is a fault on one of the circuits, it can be challenging to isolate the problem because the shared neutral can carry fault current from multiple sources. This can prolong the troubleshooting process and increase the risk of further damage. The NEC provides specific guidelines for multiwire branch circuits to ensure safety and prevent overloading of the neutral conductor. A multiwire branch circuit is a circuit that consists of two or more ungrounded conductors, hot wires that have a voltage between them, and a grounded conductor neutral wire that has equal voltage between it and each ungrounded conductor. These circuits typically serve multiple outlets or loads. Here are the key requirements. Firstly, common trip. All conductors of a multiwire branch circuit must originate from the same panel board. The circuit breaker or overcurrent protection device must open all ungrounded conductors simultaneously. This is achieved by using a 2-pole or 3-pole circuit breaker with a common trip mechanism, or by using individual circuit breakers with a handle tie to ensure they are switched off together. Secondly, balanced loads. The NEC recommends that multiwire branch circuits be arranged to minimize the neutral current. This is done by balancing the loads connected to each hot wire as much as possible. When the loads are balanced, the neutral current is reduced because the currents from each hot wire tend to cancel each other out. Thirdly, neutral sizing. The neutral conductor must be sized to carry the maximum unbalanced load. In a residential setting, the unbalanced load is often assumed to be the total load connected to the circuit. However, in commercial or industrial settings, the unbalanced load may be calculated based on the specific loads connected to the circuit. Fourthly, identification. The conductors of a multi-wire branch circuit must be clearly identified. This is typically done by color coding the hot wires A, G, black, red, blue, and using white or gray for the neutral wire. The equipment grounding conductor ground wire is typically green or bare. Fifthly, no shared neutral for separate circuits. As a general rule, the NEC does not allow the neutral conductor of a multi-wire branch circuit to be shared with other circuits that are not part of the same multi-wire branch circuit. Each multi-wire branch circuit must have its own dedicated neutral conductor. Sixthly, GFCI protection. Ground fault circuit interrupter GFCI protection is required for certain outlets in residential and commercial buildings, such as those in bathrooms, kitchens, and outdoor areas. When using a GFCI on a multi-wire branch circuit, it is important to ensure that the GFCI is properly rated for the voltage and current of the circuit. It is also important to use a GFCI that is designed for multi-wire branch circuits, as some GFCIs may not work properly with shared neutral conductors. Seventhly, arc fault circuit interrupter of side protection. Arc fault circuit interrupter of side protection is required for most branch circuits that supply outlets in residential buildings. SIs are designed to detect arc faults, which are a common cause of electrical fires. When using an FSI on a multi-wire branch circuit, it is important to ensure that the FSI is properly rated for the voltage and current of the circuit. It is also important to use an FSI that is designed for multi-wire branch circuits, as some FSIs may not work properly with shared neutral conductors. Eighthly, handle ties. If individual circuit breakers are used for a multi-wire branch circuit, they must be equipped with handle ties. Handle ties are devices that connect the handles of adjacent circuit breakers together so that when one circuit breaker is switched off, the other circuit breaker is also switched off. This ensures that all conductors of the multi-wire branch circuit are disconnected simultaneously, which is important for safety. Ninthly, dedicated neutral. Each multi-wire branch circuit must have its own dedicated neutral conductor. The neutral conductor cannot be shared with other circuits, as this can lead to overloading of the neutral conductor and potential fire hazards. Tenthly, proper wiring practices. It is important to follow proper wiring practices when installing multi-wire branch circuits. This includes using the correct wire size, making sure that all connections are tight, and properly grounding the circuit. Failure to follow proper wiring practices can lead to electrical problems and safety hazards. In addition to these requirements, it is important to consult the NEC and local electrical codes for specific requirements in your area. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. Always consult with a qualified electrician when installing or modifying electrical circuits. A qualified electrician will be able to ensure that the work is done safely and in accordance with all applicable codes. Multi-wire branch circuits offer several benefits, including reduced wiring costs, improved energy efficiency, and increased circuit capacity. However, it is important to follow the NEC requirements and proper wiring practices to ensure safety and prevent electrical problems. The fact that the breakers are not interlocked with a handle tie is a violation of the NEC. Handle ties or multi-pole breakers ensure that all hot legs of the circuit are disconnected simultaneously, which is crucial for safety when working on the circuit. The absence of this common disconnect means that someone could potentially work on one leg of the circuit while the other leg is still energized, leading to a dangerous situation. The separation of the devices by 50 feet does not change the fundamental safety issues. The entire length of the shared neutral is still subject to potential overloading and the risk of being energized unexpectedly. Here is a discussion on the NEC section 300.13 continuity of grounded conductors. Firstly, general requirement. NEC section 300.13b specifically addresses the continuity of grounded conductors, which are commonly referred to as neutral conductors. The general requirement is that the grounded conductor of a circuit must remain continuous without any splices or joints within the raceway or enclosure. This ensures that the neutral path is always intact and can safely carry fault current back to the source. Secondly, intent of the rule. The intent of this rule is to prevent the interruption of the neutral path, which could lead to dangerous voltage imbalances and potential shock hazards. If the neutral conductor is broken or disconnected, the voltage on the connected equipment can rise to dangerous levels, posing a risk of electric shock to anyone who comes into contact with the equipment. Thirdly, multiwire branch circuits. In multiwire branch circuits, the neutral conductor is shared by two or more ungrounded conductors' hot wires. Section 300.13b requires that the continuity of the neutral conductor in a multiwire branch circuit be maintained when any of the ungrounded conductors are disconnected. This is typically achieved by using a 2-pole or 3-pole circuit breaker with a common trip mechanism, or by using individual circuit breakers with the handle tie to ensure they are switched off together. Fourthly, permitted exceptions. There are a few exceptions to the general rule regarding the continuity of grounded conductors. For example, splices and terminations are permitted within enclosures, provided that they are made using approved methods and materials. Additionally, the neutral conductor can be interrupted by a disconnecting means such as a switch or circuit breaker, provided that the disconnecting means is designed to simultaneously disconnect all ungrounded conductors as well. Fifthly, prohibited practices. Section 300.13b prohibits certain practices that could compromise the continuity of the grounded conductor. For example, it is not permitted to use a single pole switch to interrupt the neutral conductor of a multiwire branch circuit. This could leave the equipment connected to the circuit energized at a dangerous voltage level. Sixthly, compliance methods. To comply with Section 300.13b, electricians must use proper wiring methods and materials. This includes using continuous lengths of wire for the neutral conductor, making sure that all connections are tight and secure, and using approved splicing and termination methods. Seventhly, grounding considerations. Section 300.13b is closely related to the grounding requirements in the NEC. Proper grounding is essential for providing a safe path for fault current to flow back to the source, which helps to prevent electric shock and minimize the risk of fire. Eighthly, inspection and enforcement. Electrical inspectors typically check for compliance with Section 300.13b during inspections of electrical installations. Violations of this rule can result in fines, penalties, and the requirement to correct the deficiencies. Ninthly, safety implications. The requirements in Section 300.13b are essential for ensuring the safety of electrical systems. By maintaining the continuity of the grounded conductor, the risk of electric shock and fire is significantly reduced. Tenthly, practical examples. Some practical examples of how to comply with Section 300.13b include using continuous lengths of wire for the neutral conductor, making sure that all connections are tight and secure, and using approved splicing and termination methods. Additionally, it is important to use a 2-pole or 3-pole circuit breaker with a common trip mechanism for multiwire branch circuits. Sharing a neutral between circuits that are not part of a properly configured multiwire branch circuit violates Section 300.13b because it compromises the continuity and safety of each individual circuit. In such cases, each circuit must have its own dedicated neutral conductor to comply with the NEC.